It
Okay,
won't be.
so I'm Zach, and here with my friend Alex.
That's me.
Yeah, that's you. And so I'm gonna be talking about something called the pancake problem.
Woo! Woo!
Oh yeah, there. So I mean, I'm gonna be talking about math, and Alex, you're gonna be my like pseudo layman or whatever, because
Yeah,
you're pretty familiar with the math. You know a decent amount of it, but you aren't like a fucking hardcore academic, and you'll be able to interrupt me and like tell me when I'm not making sense.
yeah. I'm like a fledgling, like a little
Absolutely.
bird.
Okay, so the pancake problem is so pancake problem is here's uh, it basically asks the following. So imagine you got a stack of pancakes, right? But the chef who made them was really drunk, and so like they're all in the wrong order, basically. Right? If you saw a stack of pancakes looking like this, you'd say something's off. Instead, pancakes typically, like the movies or whatever, go from smallest to biggest, right? And
Yeah,
so the question is like, how can we get from here to there in the fewest amount of steps? In the worst case, and here we're allowed like a single quote unquote step. A step is a spatula flip, i.e., we could select some portion of the pancakes. We would like look at these two, use a spatula, right, and flip them over. So flipping these pancakes would give us, it'll send us to basically this configuration. You see, it's not the bottom and top swapped, or the top and second top swapped, right? And we'd want to
and
use a number of spatula flips so that we eventually end up with the sorted thing.
slight correction.
What? Yeah?
You flipped the wrong pancake stack. The
No.
chef is too drunk. Isn't it supposed to be a slightly long, big long, little long if you're flipping from the first stack?
Yeah, I guess these two are the same order, so yeah, maybe technically it should be like this is what you're saying.
No, shouldn't it be
Well, I flipped
that
the
that
this
long line stays in the middle, right? Oh, did you flip the
I
whole
flipped the
pancake?
top two.
Oh, the top two.
Yeah, yeah. So,
I was
well,
tricking you.
all right. This the confusion here is endemic of like is a symptom of a few things. First off, my bad drawing and cluttered notation, but it's also kind of the fact that we're drawing pancakes. And so in the actual math problem on this math paper on this, they don't actually draw pictures of pancakes. Instead, we mathematicians we abstract a little bit to find something easier to work with. And I'll show you that because maybe it'll be a bit easier to communicate with. Okay, pancake problem. But
Nice.
maybe it'll be good to always keep in mind. Or well, I'll rewrite the new problem in a second. But yeah, so we're talking about the pancake problem, right? Yeah, and so mathematicians love numbers. Honestly, I think that's kind of a lie. Mathematicians aren't the craziest about numbers, but here it's useful, more useful to think about numbers than pancakes. So basically, given a sequence of pancakes, right? what we're gonna do is we're gonna convert this to a sequence of numbers. So the top pancake's the second smallest. So let's write a 2. The second pancake is the most small. So we're gonna write a 1, first small, then third smallest, and then fourth smallest. So this configuration of pancakes just becomes 2, 1, 3, 4. And it's even easier to, or maybe I don't want an arrow here. It's just this pancake is going to be considered to be represented as these numbers, and because writing vertically is silly, we're just going to write it as a list. So 2, 1, 3, 4. And so now, when we do a spatula flip on the first 2, this is just simply equivalent to looking at a prefix, some start of the list, and then reversing the order. So here, the flipping the first 2 is equivalent to doing this, right?
Yeah.
Yeah. Okay, so basically now, what the question becomes is, my eraser, or I could probably just, yeah. So the question now is, given any string, in any list, or string / list on K letters, so just something like, if K is 7, then it could be maybe 7, 1, 5, 4, 3, or 2, 3, let's say 6. So we got some list in K letters, and and so the question is, how many prefix reversals, where we take some prefix of the string and reverse it. Reversals to sort, so how many reversals do we need to get from this guy all the way to the sorted one, where we have 1, 2, 3 all the way up to 7? So that's the question. Kind of does does that make sense?
Yeah, that looks good to me.
All right. And we're just gonna call. So we're gonna let, I guess, f of k. I'm gonna say that's defined to equal.
Who's this guy?
Minimum.
I'm driving.
Hi,
You
Charlie.
should crash. Alright, where are we, Zach?
Well, Alex, speaking of f, we're gonna find f of k to be the min-max sort time of k letter string, which basically just means if I'm given any so for any string, which is just some arrangement.
Oh, Charlie Love.
So any string which is arrangement of k letters. So for any string which is arrangement of k letters, right? It says that I can use at least FK, or at most FK reversals, prefix reversals to get it to the identity or to sort it. So, because we ultimately want to get any K letter string back to 1, 2 to K in order. And so it just says, yeah, FK is just the minimum number of it's the smallest number such that given any string, I can use at most that number of prefix reversals to get to this guy.
Mm-hmm.
Is that, kind of clear?
Yeah, it's just like the minimum number of oh god, my chair. There we go. Of little steps you have to do
Yeah.
to swap a bag
Yeah.
based
Yeah.
in as a function of how
Mhm.
many letters are in the string.
Yeah, or you could think about it as you could create a graph where your vertices are K-letter strings. And here by K-letter strings, I mean some rearrangement of the numbers 1 through K in some list. So we have all the K-letter strings as vertices of our graph, and we connect them when, so maybe let's say we have 1, 2, 3, 2, 1, 3, 1, 3, 2, some other guys and whatever, 3, 1, 2, 2, 3,
2, 3, 1,
and 3, 2, 1. And so we just connect, like in our graph, we add an edge if we can use a prefix reversal to get from one to the other. So here we reverse the first 2 letters, we go from there to there. By reversing all the letters, we go from there to there. And you can continue to do this by reversing 2, we get to there. By reversing 3, we get to there.
and then 1, 3, 2 and 3, 2, 1, or 3, 1. Yeah.
Yeah, and presumably, yeah. So for this one, the graph actually looks like a cycle. Funnily enough, I apologize that I've kind of drawn over some other stuff. So it's a very unpretty graph. But so yeah, once you've drawn the graph, it's just saying, what's so this is our sorted K letter string, and it's just f of k is the means that for every other vertex in the graph, we can find a path of length f of k from it, or of length at most f of k, using at most f of k edges to reach this sorted guy here.
Is f of k here? Hold on. 1.
Yeah. So basically, all right. This is a cycle. So this is a distance 1, 2, 3. This guy has to be the furthest away. So there's a 3 edge path from here to this guy, and everybody else should have shorter because it's a cycle.
So f of k, or f of k here is, or f of 3, I guess, is 2. Or 3.
F of 3 is 3 because
3.
That guy has, because if you redrew this graph better, it would look like it just looks like this, right? And so everything can be reached with a path of 3, and that's required to reach the guy over here. But anyway, so we've got f of k, and the pancake problem is just asking determine f of k and get good bounds for it. This is such a jank.
What happened for the past hour? I seem to have forgotten.
Mm-hmm. Yeah, this is recorded. I guess they'll see that a long period of time passed in between. Yeah, and then typically when a time skip happens, you'd assume that a lot of preparation happened, and what follows will be coherently explained. Yeah, this is not the case here.
Well,
But
it's coherent. It's just it was going to be the same thing you were going to say an hour ago.
I don't know. I think you give too much credit. Maybe I'm just bad perceiving things, but like I feel it's very incoherent when I'm drawing a graph that's like
I,
this with some text behind it.
I don't know. Maybe it's just me, but I mean, it was pretty easy to follow for that.
Okay.
But
Well,
also, I write like that, so it may not help.
maybe everyone will disagree, and you're a terrible layperson because the way you process the world is awful. But I'll function on their assumption that this is not the case.
Yeah, everyone
So
gets it. You guys get it.
yeah. So anyways, hmm, okay. So okay, we stay with the problem is, and I guess here's as good a time as any to mention this fun little tidbit is that this problem has been worked on before by one William H. Gates
Who's that?
who's better known for other stuff perhaps Bill
What?
Gates.
It's
Uh,
Bill Gates?
Wait, no, I
He's
think
an
this is
attorney?
somebody else. Um,
Wait,
yeah, I
wait,
mean, this is someone
yeah,
else. I was like, that doesn't look right.
yeah, wait, he's not an attorney.
Yeah, yeah. Okay, I'm gonna just take the data. So you might have noticed, right? Okay, so this paper was written by one William H. Gates. And so it's not this William H. Gates. It's actually this William H. Gates. Who went on to start Windows and Microsoft and whatever. But he did one math paper and it was on this. And so that's what kind of drew me to this problem is that first off it sounds very nice. But also I don't know. It's cool when there's a little bit of a fame or whatever tangled in. I don't know. I find it funny or something. But that's not too important to the math, so I won't dwell on it. But yeah, okay. So yeah, the problem, yeah, is to is we're concerned about this f of k, and perfect. Okay. So, okay, we know what the pancake problem is now. So what can we say about this guy? About this f function? Well, so I'm going to quickly go over why FOK is at most, is at most 2 times k and at least k minus 1. Alright. Yeah.
Wait, is it 2 to the k or 2 times k?
2 times k.
That's crazy.
Yeah, no, it's you can get nice simple bounds. So yeah, because a lot of times in mathematics it's about getting asymptotics, like saying, oh, does this function, does some function graph, some function graph, some function f, does it look kind of like, n squared or, 2 to the n, questions like that where we got no clue what it is, or getting from n squared to maybe, n to the 0.999, and then people go crazy because you've broken the barrier or something. But here we know the asymptotic behavior of it, kind of. Hopefully, does this asymptotic behavior ring a bell with you? I guess I'll just mention in passing, big O notation.
Oh, yeah, yeah, yeah,
Yeah.
yeah, yeah, yeah.
Yeah,
Yeah.
or
I know
formally
this one. I know
means
this
that
guy.
there's
You
like
mentioned in
some,
passing though.
yeah, basically there's some
There's some
constant.
constant C that. Oh yeah, it's right there.
Yeah, some constant such that the function is less than constant times the other function or whatever. Yeah, but so yeah, here we know asymptotically that it's basically linear in k, but we don't know the constant. And I don't know, I'm very drawn to these kinds of problems because I like optimizing things or whatever. Um.
That's why they call you the puzzler.
Oh yeah, that's true. That's true.
Question, and this is irrelevant. Okay,
Yeah. No,
if
it's
you
very
wanted a
relevant. Um.
if you wanted a really bad upper bound,
Mhm.
could you say like, okay, the maximum number of permutations of k is 2 to the k, right? So at
Well,
most you would
no,
have a
it's gonna
graph,
be
or
the number
k to
of
the k, right?
permutations is k factorial.
K fact, I forgot combinatorics, but that's the maximum number of permutations of length k,
Yeah.
right? So
Yeah, it's
if you
the
thought of it as
exact
a
number.
graph, the furthest distance from one to the other, if you imagine like there's one that is so far away, you'd have to go through every single other
Yeah.
permutation. It would be k factorial minus one, or maybe just k factorial. I think
Let's
it's
see. So it would be it'd be k factorial minus one because so like in the case where if you have a connected graph on two vertices, right? Then
oh
you
yeah,
know
it'd be
you
hard
use
to
a
have a
path of you use a path with one edge, and so generally for a connected graph, if you have n vertices, then there should be a path of length n minus one. Though technically, to get this bound at all, you'd have to show that the graph, right, this prefix reversal graph, is connected, which like it is true, but if you're gonna prove that, you probably will prove a better bound than whatever you'd give. But in theory, if you assumed it was connected, which just happens to be, then you could get this k factorial minus one bound. But
nice.
for now, I'll just do the slightly better 2k bound.
What? That seems much better.
Yeah. So basically, the idea is this. So you start with some string. Oops, I gotta start with some string s, and it's gonna look like a bunch of numbers, right? It's gonna be like s1, comma, dot dot dot. Yeah. Alright. So I'm just gonna write. Yeah, this is the first. What do I? How do I want to write this? So we got some string, and it's looks like a bunch of numbers, and then the letter k is gonna appear, or the number k is gonna appear, and then some more numbers or whatever. Right. Yeah, like this is general like without loss of generality, right? We can assume maybe there's some stuff here, maybe there's some stuff there. But the letter k appears because it's a rearrangement of the numbers from 1 through k. Does that kind of make sense?
Yeah.
Yeah. And so first what we do is we'll use a prefix flip. Or so actually I'm gonna say so s is gonna be equal to some prefix string, which is just some numbers or letters or whatever. And then we're gonna have the letter k and then some suffix string and so maybe this guy should be instead of writing S here, let's write sigma. Yeah.
Yeah. Yeah.
Yeah, okay. I'm gonna erase this first quickly and then sigma. Yeah, so sigma is equal to prefix string and then the letter K and then suffix string, and both of these could be empty, so it could secretly look like so it might end with the letter K or might start with the letter K, but maybe these strings are non-empty. So the first move I'm gonna do is I'm gonna use a prefix reversal on these guys, and that will send me to K and then P prime, which is just the reversal of this prefix string, and then S. So now k is at the front. And now what I'm going to do, I'm going to do a reversal on the entire string, which will send us to k at the end, s reversed, and p back into its normal order. So what's happened here, right, is now we've spent 2 moves and we've put k at the back of the string.
Wait, can I take a little guess?
Yeah?
By induction, you could say, there's a k minus 1 in there, right?
Yeah.
And then you're like, wait, we just do that again and again, and then until you're down to k or k minus 1.
Yeah.
Uh,
Yeah.
but,
So, yeah,
until you're
one
down
way
to
maybe
1.
would be, we say this is sigma k. It's a string on the letters 1 through k. And so we can say this is equal to, we've got a k at the end, and now some string on the letters 1 through k. And now we just use prefix reversals only on this guy to sort it. And the induction thing will happen. And so each time, by using 2 more moves, we can, so 2 more moves gives us some string on the letters 1 through k minus 2, and now k minus 1 followed by k, and doing this to the end should just repeating this will give the upper bound of 2 times k, which is
That's sick.
a whole deal better than k factorial minus 1, not to break your solution, Alex. Yeah. So
That's sick. That's crazy.
So yeah, that's okay. So that's kind of our informal proof. The idea of the proof for, I don't know, that's good enough of a proof for that part, the upper bound. Now I'm gonna talk about the lower bound a little bit. That we need at least k minus 1 reversals. So why is this true? What time is it? Oh, it's 10:15. I'm starting to get tired.
Oh no. Well,
Okay, well, basically, right. Yeah?
no, go on. I want to hear this.
Okay. So, right, the idea now basically is, so we got, again, some string sigma. And now, what we're going to do, so sigma, and it's got, is we're going to say, we're going to count we're going to find A of sigma. It's going to count the quote-unquote adjacencies. So blah blah, this counts adjacencies in sigma. Right, and so basically what this is going to be considered equal is basically it's the okay, it's the number of I where the letter I, so basically where such that the position where I appears, right,
Mm-hmm.
and the position where I plus 1 appears, they're right next to each other, essentially. So either it means that basically that sigma either equals some prefix, and then I plus 1, then a suffix, or it looks like equal to prefix and then I plus 1, I, and then the suffix. Is that kind of clear?
Is I and I plus 1, are those like those are consecutive? Or no, those are just two consecutive places. Or are they consecutive
Consecutive back. Maybe it'd be better to do with an example.
So
Yeah.
like if 2 and 3 were next to each other.
Yeah. So basically, yeah, you want to see. So A of sigma basically counts number of 1 and 2, which are next to each other, and 2 and 3. So for example, if sigma is equal to let's say 6, 1, 3, 4, 5, 2, then basically we'd say that for a 3 and 4 are adjacent because they're consecutive and their values are 1 apart. And 4 and 5, again are consecutive and their values are 1 apart.
Okay.
If we added a 7 here, then they'd also be adjacent. So in this example, we have, A of sigma is defined to be equal to 3 because we got 3 adjacencies. Okay, and so the end goal is to reach this sorted kind of permutation. We want to reach the permutation which is 1 through k. So we call this the identity on k because basically you can think of strings also as functions. So where like basically it sends like where the first letter basically is what. So given a string, if S1, we're basically like the function sends like 1 to the first letter, 2 to the second letter,
Yeah.
k to the kth letter, and here each letter is sent to itself, each number from 1 through k is sent to itself, and so it's the identity. But yeah, so we want to end up here, and so it's very easy to see, right, that the number of adjacencies in id k minus 1 is equal to, in id k, so in our sorted k identity is just equal to k minus 1 because, adjacent and then adjacent, and etc.
Yeah.
Yeah, and just k minus 1. And the fact it's not k because you count the gaps in between them. I usually get mixed up by those, but it's k minus 1 here. And so to get our lower bound, I'm gonna claim that basically, if we start at some sigma, and then we use a prefix reversal to reach some sigma prime, then basically the adjacencies can change by at most 1. And also it's easy to show. So if I have, for example, something like basically something silly, like you could do the idea is that if you basically there should be also stuff with 0 adjacencies. You could start, I guess, so maybe it's not true. So if you have 3, 1, 4, 2, so maybe it's false for small k, but so for k equals 4, we have this, and then for 5, we just add a 5 here, then you add a 6, 7, 8, dot dot dot. And so for all large K, there exists some sigma where A of sigma equals 0. And so if we confirm this step, that whenever we apply a prefix reversal, that the adjacencies change by at most 1, then to start at 0 and end up at k minus 1 under this function, it would mean that we have to use at least k minus 1 steps, or k minus 1 reversals, if that makes sense. Am I going too fast?
No,
Oh,
I got it.
yeah, so it suffices to show this bit now. Yeah, okay, so let's clean this up a little bit.
You can use the lasso tool to better select, or you're gonna squeeze it. Oh.
Yeah, I'm not gonna squeeze it. I'm just gonna get rid of it. Yeah, is this the lasso? That's not the lasso. Is this the lasso?
The lasso is the one right above the eraser.
Oh, this
So
is
that
the lasso.
selects an area, and well, it looks like a square, but it's not.
Yeah, but what kind of area is this?
Well, it's so if you put things in there, it'll only select the region that you select.
Yeah, this is.
But it works weird because then it inverts whenever you loop over.
Alex, this wasn't what I wanted at all. You see, but when I do it like this, it works, Alex. Your suggestion was just ridiculous.
Yeah, you're right. My bad.
Okay. So we want to show. So yeah, if we have our sigma and we then use the reversal get sigma prime, then adjacencies of sigma minus minus the adjacencies of sigma prime.
Is adjacency 0 the worst case scenario?
Oh yeah, you definitely assume that, though we don't know for sure. Maybe, yeah, I might get into that a bit more later, but it's hard to really say much of anything about what we know can't happen, because it could be that everything, or actually no, yes, we, let me think for just a second. I think, yeah, actually, that's the worst case for the bounds we know, but we don't know. It's silly, but we can't fully rule out the case that like the worst case has some extra adjacencies in it.
Is it just for like some really large K?
Yeah, well, so basically the issue is that what if to basically in the shortest path from sigma to the identity, right? So we have some long winding path or whatever. Maybe if you start with some adjacencies, like the best way is to start destroying some of them. Or I don't know, maybe there's pedantic math stuff where like it's hard to fully rule out that kind of stuff. But
well, we're gonna make the assumption we're gonna just work with that.
No, because what I'm just saying is here's a lower bound, right? So I'm just saying that we. So this is just to sort of give in some information, because I'm just gonna say if we start with the permutation, right, and we apply a reversal, then the adjacencies will change by at most 1. And so once we've shown this, it'll mean that once we start with the guy with 0, then the only way to sort it must use k minus 1 reversals at least. And so we don't know if that's the worst case, but
It won't be lower than
we'll
that.
be able to create some guys which are pretty bad and pretty annoying to fix. Is that clear, or I can
Yeah.
explain
No, that's
more?
clear. So it's a lower bound, but it's not like the worst. It's just like there's
Yeah,
no
we
way
don't
it
know it's the
could be low.
worst case, but we know it's pretty bad.
Yeah.
Yeah. Yeah, and like this adjacency thing comes up, and like the best known lower bounds too is, that's part of the arguments and stuff. But anyways, okay, so yeah. Alrighty, so how would you show this? Well, what you
Oh, well, that's
do
easy.
is you kind of like you draw almost a picture or something. So, so we'll have, let's say, sigma, right? So sigma equals, some word P and some word S, and we're saying we're reversing P. So we send it to P prime and S. Well, so basically what happens is now, and so if you unfold this even more, this is like P1 ... PT, and this is like some letters S1 ... to, I don't know, S big T, let's say. And so that's what the letters here look like. And the letters here look like
PT.
PT ... to P1 and S1 ... to ST. So what happens is if there's any adjacencies contained in here will also be contained in here because the letters don't move around here. So the number of adjacencies on this side remain unchanged. And at the same time, if we've got adjacency contained in here, it'd also
It'll
be
also be
adjacency contained in here. It just
be backwards.
it'll be backwards, but yeah, it's still maintained. The only thing that changes is that if there's an adjacency between these two letters, it'll be broken. So, maybe in red, so that guy will be broken in this guy because they're now apart. Meanwhile, if these, so if, let's say, if these numbers would form an adjacency, P1 and S1, then when we do the reversal, we create an adjacency.
Yeah.
So we can either increase by 1 when the front letter now gets, now forms an adjacency with where it was sent to, and we lose an adjacency if there was one and now they become separated. Or it could either stay the same if nothing happens, or if we break an adjacency but form a new one at the same time.
I was thinking like if you had 3, 4, and 5, right?
Yeah. So exactly. So if we had, let's see, 1, 3, 2, and so here we have one adjacency, this guy, and if we reversed the first two letters, we will reach 3, 1, 2, where now 3 is no longer an adjacency with 2, but we now have 1 forming adjacency with 2.
Yeah.
Yeah. So okay, that establishes so that establishes this claim, and therefore, by what I mentioned before, we get the lower bound of f of k being at least k minus 1. Wonderful.
So simple.
Yeah, so simple. Okay, let me look at the script. Okay, so this is the pause time I put in the script to check in with you and be like, how's it going, Alex? Is this all making sense? Do you
Yeah.
have
Well,
any questions of where this is going?
um. Well, let me think.
Sure. I can drink some water. Mm. Delicious
I get
water.
it. So far, everything has made sense. I'll say.
That's wonderful.
Although I don't think I could think of where we're going next
Yeah.
because I feel like we've got the problem solved.
Yeah, well, we know two good bounds, right? We know, right? So the status quo, or I don't know, is that we know this function f. We apply it to k, right? So we're trying to determine this function, you know. And so we know it's at most 2 to k, and we know it's at least k minus 1. But we'd expect probably that it should be basically f of k is basically like some constant times k.
Yeah.
And so what's this constant, you know?
Well,
You know,
it's
look at all
between.
these question marks appearing around it.
Right, there's so many questions.
Yeah, you know, there's a big problem, you could even say. But yeah, so that's but basically, so we've got the basics down. We know the easy stuff. But you know, Bill Gates and Christos Papadimitriou didn't just write a paper saying these two things. They had some clever ideas to do better on both of these things. So they got better lower bound and a better upper bound. And I won't be talking too much about the lower bound, but instead about this upper bound here. Yeah, and indeed. So
I have
actually, yeah,
some comments to the chef, or
yeah,
some compliments to the chef. I think you explained the 2K thing very well.
awesome.
That was like really easy. K minus one thing. Um, uh, I I got it. I got it.
But you hated it.
No, I didn't hate it. But to the layman, or maybe perhaps a thinker who thinks the end, if it's a thinker who thinks, maybe a little bit clearer, or like on a new like blank page, something like that.
Yeah.
Like introduce it as like, well, it cannot be less than this, and then kind of more so into as to why it isn't, or it couldn't be less than
Mm-hmm.
that. Which I accept it as fact. I get it. If you told me it, I would be like, I can prove that. Maybe. Uh,
Yeah. Well, we can go over it just a little bit more, right? It's just so the claim is first that, uh, you know, so it breaks into a few parts. There exists sigma where a sigma equals 0.
mhm.
So that's one. We've got 2, which says that the adjacencies in our density is equal to k minus 1. And then the third.
Oh, wait, hold on.
Yeah.
Don't even, don't even, don't even write step three. I'm about to start thinking, Zach.
Okay.
So any super flip, or sorry, pancake flip. What do you call it?
A pancake flip.
Yeah, any or super flip, which is what you wrote. I don't know
Yeah.
if that was. Yeah, so any super flip can at most add one um whatchamacallit, right?
Adjacency. Yeah.
Yeah, right. No matter and which you showed at the end of that.
Yeah, exactly.
So if the adjacency of the identity is k minus one, and you can at most, right,
Yeah.
have a one addition per flip, and there always will exist some sigma where the adjacency of sigma is zero, then you have to do it k minus one times.
Yeah. Yeah,
I'm
yeah.
kind
So
of
basically,
like
yeah.
I'm kind of
Yeah, that's a good way to put it. Basically, yeah. So each reversal can increase a of the permutations. So yeah, a sigma, but the whatever it's being applied to changes. Can increase a the number of adjacencies by at most one QED. Yeah, but no, yeah. So you just staple these things, you string these things together, and you quickly see that it implies that f of k is at least k minus 1.
k minus one factorial.
Oh no!
You have to do upside down exclamation point. Espanol. Okay, see now I'm like the ultimate understanding.
That's
Now
wonderful to hear, Alex.
this was in my
And
head.
I'm sure the video watchers will be feeling the same way.
Yeah, I think they'll get it. I don't think anything has been like fusing. Well, once it's been clarified, it's like, oh yeah, that's like you just got to think about it.
Yeah, yeah.